is again finding the equation of a straight line. Okay, so I'm going to teach you method number 2. You decide what you want to use. Okay, both the answer will be the same. Okay, so now our method number 2 is we know. So I'm going to sketch. Okay, so we know stress A. I can't remember what's the value already. It's equal to 41.667. Okay, so I'm going to okay. So this is our point A, and this is our point B. Okay, and we know that at point A the stress is 41.667 positive. Okay, so I'm going to sketch. Okay, so this is 41.667. Okay, so we have to now, if you're going to use the alternate method, you need to find what is your stress X at point B. Okay, so stress X point B, we know the y-intercept is 1 to 5. Oh, sorry, not the y-intercept. The axial load is 1 to 5. And then we have to write down the my. So my is 800 multiplied by 2 divided by IYY, which is 9.6. I've not put in the plus or minus yet because I don't know whether is it positive or negative yet. Okay, so this will be 540 multiplied by 0.9 and then divide by 1.944. Okay, so let's look at my at point B. So if we look at this graph over here, this my is going to induce a compression, right, at point B. Now we are focusing at point B. So it's going to induce a compression. Okay, so this is minus. And then moment about Z. Okay, moment about Z at point B, right, is also going to induce a compression. So both are in fact minus. Okay, so this is equal to 125 minus by 800 times 2 divided by 9.6 is 800 times 2 divided by 9.6 equal to 166.667 and then minus by 250. So it's equal to 125 minus 166.667 minus 250 is equal to 291 minus 291.667. Okay, so I'm going to sketch 291.667. Okay, so I'm going to, so 50, 100, 200. So it's somewhere around here. Okay, so this is minus 291.667. So now if we were to draw a straight line, right, from here to here, we have to find what is this position X, right? And we know that the entire distance, right, from here to here, we know the entire distance. Oh, let me use a different color. I do apologize. So we are aware that this is X. X is where it actually intersects or where the normal stress is equal to 0. And then we also know that the distance from here to here, we know that this is 4 inch, right? So if we were to find the gradient, which is equal to the change in y over the change in x. So the change in y is equal to 41.667 divided by x, and the change in y, 41.667 minus by 291.667, and that is the entire length. That's 4. Okay, so this will be equal to, so x will be equal to 41.667 multiplied by 4 divided by 41.667 plus by 291.667. Okay, so this will be equal to 1.667 plus 291.667. So 41.667 times 4 divided. So this is 0.5 inch. Now this 0.5 inch is from point A, right? This is using method number 2, right? So if you go up to here, our answer is 0.5 from centroid, 1.5 from centroid, I mean. So this is where our y-intercept is, right? And then the distance from here to here is equal to what? 2 minus 1.5 is also equal to 0.5 inch. So it's the same thing, okay? The answer is the same. Again, you decide what you want to use. I'm fine with either method, okay? If you can remember the formula and remember your vectors, you use equation number 1. If not, you use a simpler way like what I've shown you in method number 2. Equation of straight line, just looking for a gradient, you can find the y-intercept is so much more easier, okay, if you cannot remember the formula. Okay, so this is the end for bending moment. So what I want to start now is we're going to go into a new chapter, okay. And this chapter is, if you ask my point of view, is the most complicated, okay. Buckling was not that bad. Buckling is just plugging in formulas. It's pretty straightforward. Shearing stress is one of the worst, okay. In solid mechanics, shearing stress is one of the most difficult topic. But don't worry, I'll make sure you go through, okay. So we'll look at shearing stress. Okay, so what do we mean by shearing stress? So shearing stress are stress or are stresses acting parallel, okay, to the surface. So there's two way we define shearing stress. Okay, so if we were to draw our transformation over here, this is x and this is y, and if I were to have an element, right, the stress over here this is shear xy. Okay, so why is it shear xy? Okay, the first x over here is the intersecting plane. Okay, let me elaborate what do I mean. Okay, if you were to look at this plane that I'm shading in yellow, right, this plane intersect the what? Happen to intersect the x-axis, yes or no? Right? So the first one is the intersecting plane. So the plane, okay, so this plane intersect the x-axis. Okay, and then you see the next y over here. This y defines the direction or the direction of the shear stress. Okay, so for this case is vertical, that's why we call it y. So if we were to draw another arrow over here, right, this is known as shear yx. Okay, and why is that? Because the plane intersecting the transformation is on intersecting the y-axis. So I'm going to highlight this in green, right? If you look at this axis, so if I were to draw a green over here, right, and draw a line, right? So this is the plane intersecting the y-axis, right? And the direction of the shear stress, right? This is the x direction, right? It's moving towards the x. So that's why we call it shear yx. And there are only two configurations. Okay, so shear stress and shearing stress have two configuration. Okay, so what are they? Okay, so the two configuration are as follows. Okay, so we only have two configuration. The two configuration are as follows. So again, I'm going to draw my transformation. So this is x and this is y. There's only two configuration. Let me show you what are the two. So we have the first one over here. Okay, and I'm going to draw another square. So what we have over here on the left hand side, you can have shearing stress looking like this. Or shearing stress looking like this. There is no other way except these two. So this is your shear xy. This is your shear yx. And this is your shear xy. And this is your shear yx. Okay. So on the left hand side, this is what we call positive shear. And the right hand side, we call it negative shear. Okay. So if we look at the deformation pattern that I'm going to draw in orange, in positive shear, this is how your structure will deform. And then in negative shear, this is how your structure will deform. Now, both positive shear and there's no good shear, okay? Both are as good and both are as bad. There's no such things that positive shear is better than negative shear or negative shear is better than negative shear. No, okay? They are both as good or they are both as bad, okay? It's not like normal stress. brittle material can withstand higher compressive stress, cannot take tensile stress. Okay, there's no such thing in shear. Right.